Gain boosting in common source amplifiers. We have seen a common source amplifier with a constant current source as load, as shown in 1, that is T1 is an NMOS, input is given to Vin, that is the gate of T1, output is taken at the drain of T1, and we have a constant current source as load. The gain of this circuit is given by minus GM1 times infinity parallel with RDS1. So the gain is minus GM1 times RDS1. How do we further increase the gain? By using circuit 2, where the load is a constant current source. We have a T2, which is an NMOS whose gate has a constant bias voltage VB, and T1 is an NMOS whose gate is provided by the input voltage Vin. Output is taken at the drain of T2. So the gain of this circuit is given by minus GM1 times R out seen at the output node, which is nothing but the R out seen up, that is infinity for a constant current source, and R out seen down, which is nothing but RDS1 times gain of T2, that is GM2 RDS2. So the gain of this circuit is minus GM1 times RDS1 times RDS2 into GM2. So in this circuit we have further increased the gain compared to the first circuit. So how do we further increase the gain? That is, this can be done by using a concept called as gain boosting. Here the input voltage to T2 transistor is connected to an amplifier whose gain is given by minus A dash. So this is an inverting amplifier. The input to the inverting amplifier is given by the source of T2. So here, if the source voltage is at Vx for T2, then the gate voltage will be minus A dash times Vx. So here, what is the gain of this circuit? The gain of this circuit is given by minus GM1 times R out seen at the output node, which is nothing but infinity parallel with the R out seen down. R out seen down is nothing but RDS1 times GM2 RDS2 times A dash, which is shown here. So the gain of the circuit is minus GM1 times RDS1 GM2 RDS2 times A dash, which is shown here. So the gain compared to the previous circuit is further increased, and it is multiplied by the term A dash. I will further explain how the R out of this circuit is given by RDS1 times GM2 RDS2 times A dash in the next slide. So let us consider the circuit, that is the inverting amplifier with gain boosting. Let us draw the small signal model of this circuit. The small signal model of this circuit. So we have gate G1, which is given connected to Vin. So G1 connected to Vin, source S1 is grounded. Then we have D1, which has a voltage Vx. So this is D1, which is equals to S2, that is the source of transistor M2. So we have current flowing from drain of D1 to source of S1 given by Gm times VGS1. So this is the current flowing, and then we have RDS1, that is the output resistance of transistor M1. Next is gate G2. G2 is given as minus Vx times A dash because of the amplifier minus A. The source of G2 is nothing but Vx, which is shown here. Then we have drain of D2, which is here. We have a current flowing, that is GM2 times VGS2. The current will be flowing in this direction. Since the bulk of transistor M2 is not connected to source, we have a source to bulk voltage, that is VSB. Hence the term GMB2 times VSB is present. That is a constant current source, voltage controlled current source. And then we have RDS2, that is the output impedance of transistor M2. Then this node D2 is connected to a constant current source. For small signal analysis, we make the constant current source as open, since R out of it is infinity. So this is the small signal model. We want to find the R out of this circuit. So R out is found, it is equal to V out by I out, given Vin equals to 0. So we short V into ground, which is shown here. We short V into ground. So here G1 is grounded, so S1 is grounded, so VGS1 is 0. So this current source, voltage controlled current source, is an open here. Now let us find R out. So R out of this is given by, let us find V out. V out is nothing but the current I2 times RDS2, that is voltage drop across RDS2, times the voltage drop across RDS1, that is nothing but I out times RDS1. Here the current I out gets divided into I2, and then GMB2 VBS2, and then GM2 VGS2. All these currents gets added to get back our I out current, which flows through RDS1, since GM1 VGS1 is an open in this case. So V out is nothing but voltage drop across RDS2 plus the voltage drop across RDS1, which is given by I2 times RDS2 plus I out times RDS1, which is written here. So what is I2? I2, if we apply a KCL at this node, I2 is nothing but I out minus GMB2 VBS2 minus GM2 VGS2, which is written here. I2 equals to I out minus current flowing through this node, that is GM2 GMB2 VBS2, minus the current flowing through this node, that is GM2 VGS2. So what is VGS2? VGS2 is nothing but gate voltage G2 minus source voltage S2. So your gate voltage is nothing but minus VXA, and source voltage is Vx. So VGS2 is minus VXA minus Vx, that is shown here, which equals to minus Vx times 1 plus A dash. And what is VBS2? VBS2 is nothing but source voltage is at Vx, bulk voltage is at ground, so VBS2 is minus Vx. And what is Vx voltage? Vx voltage is nothing but the drop across RDS1, that is I out times RDS1. So Vx is I out times RDS1. Taking this equation, that is V out equals to I2 RDS2 plus I out RDS1, and by substituting I out value, which we obtained here in this equation, we obtain V out equals to I out plus GM2 into Vx into 1 plus A dash plus GMB2 times Vx times RDS2. So this is I out, this is I2 times RDS2 plus I out times RDS1. We know that Vx is equals to I out times RDS1. So in this equation, replace Vx by I out times RDS1. So here Vx is replaced by I out times RDS1, and this Vx is replaced by I out times RDS1. Now write V out by I out. This is nothing but 1 plus, so this RDS2 comes inside, so RDS2 plus RDS1 plus GM2 RDS1 RDS2 times 1 plus A dash plus GMB2 RDS1 RDS2. So this is the equation we get for R out. So R out, in this equation we know that RDS1 is a small value compared to this and this value. RDS2 is also a small value compared to this and this. So we can write R out, we can neglect RDS1 and RDS2 and write R out equals to RDS1 RDS2 taken as common times GM2 times 1 plus A dash plus GMB2. Here we can neglect GMB2 to be a smaller value when compared to this value. So we can write R out to be equal to RDS1 RDS2 GM2 times 1 plus A dash. Approximating 1 plus A dash to be equal to A dash, we can write R out equals to GM2 RDS2 RDS1 into A dash. So R out down in this circuit is given by GM2 RDS2 RDS1 times A dash. The gain of this circuit A is given by minus GM1 times RDS1 RDS2 GM2 times A dash, which is written here.